Hello, and welcome to Aggressive Physics. Today is day 123, and what I'd like to do today is discuss Kirchoffs Laws. Now, these laws were written by Gustav Kirchoff in 1845, and what he did is he wrote a book called The Laws of Closed Electric Circuits. And in this book, he discussed how charge and energy are treated in a circuit. Now, discussing series and parallel circuits, we've already done this. But what we have are terms that go with the different rules to have a term to define what is happening. So we have what we call the loop rule and the junction rule. And those apply to conservation of energy and conservation of charge, respectively. Now, we call that Kirchoff's first law the voltage loop rule. And what it says is anytime we have a loop in a circuit, the voltage that is gained by the electrons through the power supply has to be used up by the components as the electrons travel through the circuit. Now, we discussed that when we talked about the series circuit. In fact, the equation Vt equals V1 plus V2 plus V3 is Kirchoff's loop rule. Now, the reason we have a specific and separate rule other than saying series circuit is because some circuits are a combination of series and parallel, and we call them complex circuits. When we have complex circuits, some sections can be series, some section can be parallel. And when we have that situation, what we find is that you can't just apply the series or the parallel equations to the circuit. Certain parts apply to series and certain parts apply to the parallel. So what we can do is use the loop rule for any loop in a circuit. Now, what we'll do is anytime we have a battery, we're going to gain energy. And anytime we have a lamp or a resistor or some kind of component that uses up energy, we drop voltage. So we call those voltage drops. This is basically an example of conservation of energy. Any energy gained by the electrons has to be lost by the time it gets back to the battery. And we call that Kirchoff's first law, which is the loop rule. Now, Kirchoff also has a second law, which we call the junction rule. And anytime there's a junction in a circuit, the total charge entering the junction has to equal the total charge leaving the junction. So if 5 amps of current flow into a junction and 2 amps flow down to the first resistor in parallel, the rest has to go to the other parts of the circuit. It could be a single resistor or more. So that means if we had 5 going in and 2 going out, the other side has to have 3 amps going out. The way this works mathematically is what I do is I'll put all the arrows going into a junction on one side of an equal sign, and I'll have all the arrows going out of the junction on the other. So current in equals current out. This is conservation of charge. We already discussed this when we talked about the current flowing into the parallel circuit and then leaving the junction. The 4.4 amps in our first example during the notes was in, and the 4.4 amps had to be out. So each of the 3 pieces in our parallel circuit had to add up to the total in the battery. That means we can't create charge in the middle of the circuit, and we're not going to lose charge in the middle of the circuit. In fact, the total charge of the circuit has to add up to the total charge of the components. So, conservation of charge is merely the junction rule. Conservation of energy is the loop rule. And this can be applied to complex circuits. And what I'd like to do now is apply it to a problem that's a little more difficult than a single loop or a single junction. So let's take out the whiteboard now and solve what I consider to be a complex circuit. Remember, if we want to find the current leaving the battery, we have to simplify it to a single resistor. And then we can do V equals IR to find that. If we don't have that opportunity, what we can do is loops and junctions, knowing what we already know, in order to solve for the pieces of the circuit that we are looking for. In any circuit problem, I'm going to look for I, R, and V for every component. And if looking for brightness, I'm going to do P equals VI at the very end. I look at circuit problems as puzzles. And if we know all the pieces of the puzzle, the V, the I, and the R, and even sometimes the P, we can solve for any of the unknown pieces. So let's take out the whiteboard now and use Kirchoff's loop and junction rule in order to solve a complex circuit. Thank you. Now, what we've been doing so far is looking at series and parallel circuits separately. And what we can have are complex circuits where some of the circuit is in series and some of the circuit is in parallel. And that's where Kirchoff's laws come into play. There are two. Kirchoff's first law is what we call the loop rule. And it deals with voltage. And basically, that was when we dealt with the series circuit, how all the voltages had to add up to the total. So we have 120 volts here. The electron is energized. It has that much potential energy. When it goes through the first, it loses some. So let's say it loses 35 volts. Through the second one, it loses 70 volts. Well, assessment problems will ask, what's X? And the way you're going to do this is 120 minus 35 minus 70. And what's left over is 15 volts, and that has to be the voltage drop across that last resistor. Now, the way voltage works is you gain energy through a battery. So this is a gain, and this is a drop. And if you think of potential energy, you have an electron at 0 potential. It gains the 120, and then it has to drop and drop and drop back to 0 as it goes through the circuit. It has to have no energy when it gets back to this point so that it can be re-energized. We're not going to get extra energy, or that would be gaining something for nothing. Now, this is conservation of energy. And no matter what loop you have in a circuit, if you go around a complete loop, the energy of the loop has to be conserved. So the voltage gains have to equal the voltage drops. So that's Kirchoff's first law, known as the loop rule. Now, Kirchoff had two laws that were important in what we've been doing, and the Kirchoff's second law dealt with the parallel circuits, and it's called the junction rule. And basically it says the current into a junction has to equal the current out. And that is conservation of charge. Now, if we remember back to our parallel circuit, we'll just look at a simplified parallel circuit here. We have one junction right here. So we have 2 amps leaving the battery. If 0.5 amps flows through this section, what has to flow through the other section? Mathematically, you could do this. Everything pointing in, 2 amps, has to equal everything pointing out. 0.5 amps plus X. You could have done this in your head, I'm sure, but X would be 1.5 amps. You can't lose charge just by turning. So the total charge has to be conserved. And that will happen every time you have a path where there's a choice in a circuit. Now, if we look here at the bottom, we have 1.5 amps coming in. We have 0.5 amps coming in, and they have to combine to form 2 amps. So 2 amps goes into the battery, 2 amps leaves the battery. So this is Kirchoff's second law. It's based on what we discussed in the parallel circuit section. Now we'll look at a sample problem or two dealing with Kirchoff's laws. All right, what we're going to do now is solve this complex circuit that's a combination of a series and parallel circuit. These two resistors are in series, which is then in parallel with the 5 ohm, and they're connected to a 12-volt power supply. Now, the first thing we want to do is find the current leaving the battery, and we need to simplify it in order to get a single resistor. So it's going to be a 12-volt power supply and then some equivalent resistance. Now, you cannot just add the three together. If you have a junction, you're a parallel. If you have no junction, no choice, you're in series. So what you often need to do is go as far from the battery as possible, and you work your way in to simplify. Now, what that means, I'm going to take this 10 and 15, and I'm going to simplify that. Now, these are connected in series. 10 plus 15 is 25 ohms. So when I do that, I end up getting the following. I have a 5 ohm here, I have a 12 volt here, and this is the first step to simplifying the circuit. Now these two are connected in parallel. So what I can do is 1 over RT equals 1 over 5 ohms plus 1 over 25 ohms. So I do 5x to the negative 1 plus 25x to the negative 1, and I find the reciprocal. And I get 4.2 ohms. That's this value right here. So I've simplified my circuit to get a single resistor. And what I'm going to do is erase this so that we can expand it back and calculate more of our unknowns. Now in this case, once I have a simplified circuit, I'm going to do Ver 12 volts equals I times 4.2 ohms. 12 divided by 4.2 is 2.9. So 2.9 amps flows from this circuit, which is equivalent to this circuit. So that means 2.9 amps flows there. Well, if I look at this, now I have some choices. I could do a loop rule. I could do a junction rule. I'm going to do a loop rule here because it has a single resistor. And the loop rule said that if I gain 12 volts, I have to lose the same amount going through this resistor. So it has to take all the 12 volts. V equals IR. 12 volts equals I times 5 ohms. 12 divided by 5 gets me 2.4 amps. So this here is 2.4 amperes. Now, I can go back to a junction. At the point at the top, I'll call it junction A, I had 2.9 amps going in, 2.4 amps going down. What's going to be left to go to the other two resistors? Well, 2.9 minus 2.4 is 0.5 amps. So that's flowing here, 0.5 amps. Now, if I know the current and I know the resistance, I could do Ver again. V equals IR, 0.5 amps times 10 ohms, and 0.5 amps times 15 ohms. Now, why do they each get 0.5? Well, they're in series, so they all have the same value for the current. So 0.5 times 10 is 5 volts, and 0.5 times 15 is 7.5 volts. So we have 5 volts and 7.5 volts. So that means that we have our current flowing through each section. We have our current flowing through the original. And what we can do is ensure that we have the proper amount of voltage in each section. Now, since this and this and this section are in parallel, they should all have 12. We calculated it to be 12.5 because we rounded at this point back here. So because of our rounding, it's going to throw off our values a little bit. But what ends up happening is we can figure out the voltage, the current, and if we wanted to, the power of each section. So that's our complex circuit. Now let's put our Kirchoffs laws into practice. What we have here is a complex circuit. We have a 12-volt power supply connected to a 24-ohm resistor and then a 12 and a 36-ohm resistor. What we need to remember is that in order to figure out the current flowing from this point here, we need to simplify the circuit into a single resistor. And we need to find RT. Now, the way we do that is we need to use both the series and the parallel laws. And the way it works for most resistors is we go as far away from the battery as possible, which are these, and then work our way back to the beginning. And that's part of our accordion. We smush it together and then expand it back out. Now, how are these connected? Well, if we don't see a junction, it means they're connected in series. So these two are connected in series. Now, how do we combine series circuits and get a single resistor? Well, we add them together. So RT is 12 ohms plus 36 ohms, which is going to be 48 ohms. So this resistor here is 48. And then that's connected here to the 24 ohm resistor. This is equivalent. Now 48 and 24, they're connected with a junction. So we're going to have to do 1 over. So 1 over RT equals 1 over 24 ohms plus 1 over 48 ohms. So I'm going to do the following. 24 reciprocal, so x to the negative 1, plus 48, x to the negative 1, and find the reciprocal of that. The reciprocal was 0.0625, so 0.0625 to the negative 1 gets us 16. So RT is 16 ohms, which means this here is 16 ohms. Now let me get rid of this so we have some room to work. And RT is 16 ohms. Now, if we have 16 ohms, we could find the current leaving the battery. And we use Ver. Now, V equals IR is the most versatile equation we have. But putting the right variables into the equation becomes the difficult part, not using the equation. If you do 12 divided by 16, I should have been able to do this in my head, I get 0.75 amperes, which is the same as what leaves this battery. So we expand the circuit back out. Now, when we do that, we realize that the 0.75 comes here, but then splits up. And we don't know how much it splits up. But because this is connected to nothing else, we can use the loop rule to figure out what has to be taken from this resistor. We're energized up to 12. We go around. There's no other component. So how much voltage has to be stolen by that resistor? All 12 volts. So we know the voltage is 12. We know the resistance. What can we find? We can find the current. Once again, Ver, 12 volts, I, 24 ohms. Now this one I can do in my head. 12 divided by 24 is a half. So if half an amp goes through here, what's left to go through the other two? Now that's a junction rule. What you'll find is you'll go back and forth between the loop and the junction, the loop and the junction, when you solve more of these problems. 0.75 goes in, 0.5 goes out. What has to be the other amount going out? 0.25 amps. So this here has to be 0.25 amps. Now that's going to flow through here and here because it's a series circuit. Now we know the current. We know the resistance. Look at this. We Ver it up again. 0.25 times 12. 3 volts for this one. 0.25 times 36. 9 volts for this one. Wait a second. What do these two add up to? 12. And if we just look at these as a single entity, the total voltage in every section, because it's parallel, has to be 12. So the beauty of the circuits is that you can always constantly check and recheck your work to make sure you did it properly. So here's a complex circuit. We found the current, the voltage drop, and the resistance of each of the 3 resistors. If we wanted to, we could do P equals VI to find the power. The bigger the power, the brighter the bulb. But in this case, we just have resistors, so we wouldn't have a brightness question. It would have to be reserved for lamps.